Thanks for the invitation. Thanks for coming. So in particular, thanks to the people who actually did the work. 4 of those were supposed to be here. 3 of them are here. Just talk to them. Whatever I don't get right, they get right. Let's begin with something like background and perspectives. So the first part of background and perspectives are 3 alternatives that I want to sort of quickly touch in my talk. So the first one is about, sorry? Can you say it again? I didn't hear. Oh, it was not communication. I'm wild for communication. Please interrupt. I like that. So the first one is between work that is done by a consortium, and I'm showing the Cologne Cathedral because that was sort of took 500 years to build. So the people who first built it, most of the people who built it never knew that this would be finished, right? And a lot of scientific projects are like that, and in some sense, CASP, if you want, could be seen like that. And there's sort of this other image here where clever people like you sit in your room, or in this particular case under a tree, apple falls, you have the idea. That's a different type of science. The other alternative I'm looking at is large-scale computing. This is one large building, and in this building, to see the dimension, in front of this building is a bike here. That's this bike. And I want to talk about the difference between large-scale computing and bike computing, as I call it. And the third alternative here is one between this magpie painting here, so that's the magpie, from Claude Monet, and the same painting as an average grayscale of the painting. A little bit less detail. Okay, when we look at AlphaFold 2, this clearly is a consortium. It's full of new ideas that change the world because of cleverness. There are many people involved. There's a foundation for it, and one very important foundation is evolutionary information. So what is this idea of evolutionary information? What I'm showing here is number of residues aligned versus percentage sequence identity. If 2 proteins are naturally evolved in the blue realm, they have a similar structure. Let me pick a point. You have 100 residues aligned. 33 of these 100 are identical. These 2 proteins, if naturally evolved, designed, have similar structure. Okay? Now you go to the lab, you change 5 residues, you knock out the structure. How come nature can do 67 and you cannot, or I cannot do 5? That has to do with my ability to do experiments. That's why I'm a theoretician. So I can mess things up very quickly. But why can nature do that? Because nature has a lot of time, and the only thing we see, this is not a statement about sequence space. This is a statement about the subset of sequence space that has survived. Okay? Now this is very crucial, because it means when you look at the particular 67, that a particular protein can be exchanged, they reveal information about structure and function. That's sort of the new language that was introduced a few years ago by Chrysander and some younger version of I. So put that into a neural network. That was sort of the first time evolutionary information was combined with machine learning. And thanks to CASP, thanks to Christoph, who is here from that sort of was put out to the world, and the non-believers were flattened. So it's the beginning of it. But that's still the same concept underneath evolutionary information in AlphaFold. There's this little but. It's a family average. It's a little bit like this one here, rather than this one. That didn't matter before AlphaFold 2, because our prediction methods were so poor that we gained from this averaging so much that was good enough. That has changed. And that gets us to the protein language models. One of the people who unfortunately cannot be here is Michael Heinzinger. And they go back to what in natural language processing are language models. The simplest version of it, you have a sentence, all science is, that's the input here, so 3 words, and the output should be the next word in that sentence. That's a tool called Elmo. So in this particular case, there's a rank list of probability. In this particular case, the answer is communication. It's the highest probability. All science is communication. Okay? What we did is we simply took the same software, which essentially changed nothing, very little in the parameters. The only adjustment is we called the word an amino acid, and the sentence, if you want, is a protein. Why not domains? Why did we do that? Is a longer discussion afterwards. Let's just say that is one way of doing it. And I'm going to present that way. So in comes sequence, and we predict the next letter in the sequence. The next version, the transformer style of the protein language model, PLM, is you gray out some amino acids. So you're not predicting the next one, but you're predicting the ones that are grayed out. Slightly more interesting, slightly more complex. How much do we gray out? We take that from natural language, 10%, 15%. We didn't optimize that, and I'll get to the point why we didn't optimize that in a moment. So essentially what we then create is a situation where you get in with sequence, you put a big computer, you burn a lot of energy, and then you get out with sequence. Great, huh? So here I wasted a lot of resources. In fact, I'm sort of a little bit ashamed that we have never used as much computing. I've been using machine learning for 30 years of my life, and I've always used all the computers I could get my hands on. But this was the crown to everything I've ever done, and I'm a little bit ashamed of it. So what's the point? The point is that the PLM somehow, and we'll refer to this word of embedding, learns the language of life, learns the grammar of protein sequence. That's the hope. How can we test that? Well, ultimately, let's first, again, the idea would be if I train on a large data set, and incidentally, UniProt is too small for these language models. You need something bigger, such as Johannes's BFD here, from Johannes and Martin. You extract that information, and then you put the extracted information as input to some other devices. That's the idea. So these things are now as advanced to simply say that from now on, anything other than using embeddings as input is like using that plane to go to New York from here. Total nonsense. The days are over. You can do it wrong, and then maybe going back to nonsense is the right way of doing it because you don't know how to fly the jumbo jet or something like that. But there's an actual way to use proteins to predict anything with machine learning. Protein language models are it. What are embeddings? Embeddings essentially are the last two layers, last hidden layers of these devices that learn the language. Why last hidden, last two? I can explain that. Why is the number 1024? That's just the size of our model. Today we had somebody, we use the biggest model, so some people like big. I talked to some other people who said we use the smallest model. Some people like small. And sometimes these people who like this or that have a good reason for it, and sometimes they don't. That's life. There are two types of embeddings here. One is the per residue, one the per protein. Per residue, essentially that's the sequence. So I have a protein that's only 8 residues long in this particular case. And in this particular case, I don't have 1024 for my embeddings, but I have 4. So in this particular case, you have a matrix of 8 times 4 that represents at every single amino acid position, every single residue, you have 4 numbers, right? And then you could do a per protein embeddings. How would you do that? Well, the dumbest thing you can do is what the people in ML call pooling. The dumbest thing is you average over each dimension of the embeddings. Does that make sense? We have no idea whether it makes sense. We try it out, it works, so it does make sense. And now we can explain to you why it makes sense. We didn't know before. So all these explanations are nonsense. But one way to check whether these embeddings work at all is you look at these t-SNE plots. Here's one of those. And I have to begin to rush already. So that's why I sort of skipped that plot. I'm going to skip a lot because I completely underestimated how long it takes me to get to these first 50. Am I in 50? No. So one of the major things about doing these protein language models is to choose the correct one. Choosing the one that fulfills the original task best is not the right choice. The right choice is to choose the one that is most generic, that solves a large number of very different tasks. For instance, we looked at secondary structure prediction because this is per residue task, and we looked at location and membrane protein, is some protein a membrane protein or not, simply because all these tasks are on a very different level. And we try to find something that is good for all of these. When we look at these different language models, the next question is the biggest one best? I'm not showing you the biggest one. I'm showing you here some measure for accuracy for secondary structure prediction, but it doesn't matter. It's just one example here. What I'm showing here is number of samples. And each point here is a different protein language model. Okay? And you see sort of a correlation. Some of these models here are large and some of them are small. If I plotted here the size of the model, you would see no correlation. You only see a correlation with the number of samples I present. So all I need to do is train them long enough. If that's the case, why don't I train them long enough? Any idea?
You don't want to wait until you die.
That's sort of not a nice statement, but yeah. I run out of money. It's much simpler. So I spend a lot of money on that, but I run out of it in a very short period of time. Less than 2 months, I can burn through a lot of, by the way, TPUs. So this could have only done, we could do that only on Google hardware. So we still have not been able to reproduce this without naming certain companies. We still, so far it needed to be TPU. Let's keep it like that. So these systems are by no means at the point of overtraining. We are way below that because we would love to overtrain. We would love to come to that point, and we have another model that is closer to that, but still. Anyway, so these are the systems. Now what can we use them for? And Konstantin is here. So his method essentially tries to predict 3D structure, and Konstantin had one of those wonderful careers. He tries his first publication, AlphaFold 1 comes, he tries his second publication, AlphaFold 2 comes, and every single time he's a slow guy. He's behind these guys from DeepMind. So he is one, and they are only 150 or something like that. He still doesn't manage. But anyway, our point is we need some point what we can do that they cannot do. And what we can do is ride a bike. 150 people cannot sit on a bike from Google. So we do bike computing. What does it mean? Essentially, in terms of the way we do it, we go from query sequence directly to a 3D model through embeddings. That's all we do. So that's in this image from Konstantin here, illustrated. Now, I said there are the per residue and per protein embeddings. There's something else. That's sort of 2D embeddings. The 2D embeddings, here's the sentence, the animal didn't cross the street because it was too tired. What is this it here referring to? The street, the animal, or whatever, right? And that is sort of a relation attention had. Attention is all there is. Google introduced that. And here the idea is essentially how is a particular amino acid or letter in a sentence influenced by all the others? And that's exactly what we use for distance prediction or for 3D prediction. What Konstantin shows here is for different generations of language models. That's the correlation of predicted and observed. High is good, low is bad. The violin plots. Essentially what we see here is what the best you could do in 2019 is here. That is what you can do state of the art is sort of AlphaFold 1, okay? There's nowhere near AlphaFold 2. This is sort of the state of the art of the traditional way of doing it before AlphaFold 2. And you see that only at the point of 2021, so when the language models evolved to the transformer, when we use BFD, only at that point do we become competitive, okay? That's one reality. The other reality is we're trying to make it small. How can we do that? So I said these attention heads, these 2D embeddings, they're important. There are 768 of those, and we see the performance is this one here with 768. It is lower if I take only 100. But we say this difference is not significant, and 100 is 7 times faster than 700, so we take 100. This is not going to make me win in CASP, because we are explicitly not selecting the best thing. We're selecting the one that we feel is a good compromise and we want to gain speed. The same thing we do in the size of the network, so we pick something that is 10 times smaller, and that still has an okay performance. At the end of the day, let me point out the first thing. What you see here is an interdistance map of raw embeddings, nothing trained. This thing here had only ever seen sequences, no structure. I'm not saying this is a good distance prediction, but I'm in CASP long enough. At some point we competed, and our best prediction method was not as good as that. That's raw embeddings. There's no structure, there's no optimization, right? Just learning sequences, that thing here. Then comes an optimization, then it looks a little bit better. Main point, nowhere near AlphaFold, nowhere near the CASP winners. But, you know, the first point is if you remove the alignments that we have, if you pretend to remove the alignments, this sort of thing works actually better than AlphaFold 2. The next idea is one about how good do I have to be sort of in business. 16 minutes. I have 16 minutes done. Okay. So how accurate is enough? That's pi. 3.2 is pi as defined by the Parliament of Indiana in 1887. So there was the political representatives decided pi is 3.2. This is sort of what I remember in my head. This is what NASA needs to fly satellites. This is what we know, 62 trillion digits. What do we need that for, right? That's sort of most likely the most important, other than sort of computer safety, that may be the most important number of digits you can use. So what if we have less accuracy and we sort of help the planet by consuming less energy? Is there a way to do that? And of course, if I make a random prediction, I'm really, really fast and I save a lot of energy, and that's nonsense. So I have to have a good compromise between these two, and I'm not sure whether we have that, but we are sort of trying to say there's one part of a compromise that we have. And this goes back to a tool that was presented 2 days ago or whatever by Johannes, fold-seek. And as you all know, I'm not sure whether Johannes was clear enough about doing that, there was a time when people used sequence alignment. That's over. So after AlphaFold came fold-seek, and since fold-seek we can replace alignments by structure searches. We do AlphaFold against AlphaFold and replace alignments by fold-seek. Thanks for that tool. It's an incredible tool. And what I'm going to look at here is if rather than putting AlphaFold into that tool, or rather than doing actual 3D structures, I put Ember 3D in, how much would I lose? And again, I'm a little bit too pressed in what I want to show you. The black line is using 3D experimental structures, and that is using Ember, and that is using MMSeq. So that's using sequence alone. It's one of the state-of-the-art methods using sequence alone. So way, way better than sequence alone. Not as good as using 3D structures, but pretty close, you could argue. Okay, maybe we are close enough. The next thing, this is really fast. I don't see Dina in the room, so this is not 100,000 times faster than AlphaFold, but it's sort of close. It's very, very, very fast. What does speed buy me? So ESM fold is faster than AlphaFold. They can do 600 million, where AlphaFold can only do 200 million. They paid less money for it, blah, blah, blah. Is that worth it? I don't know. So the interface of ESM fold is really cool. But speed matters, obviously, if it is used well. What is used well? Well, one idea could be to predict the effect of variance, single amino acid variance. Here are 4 different structures. That is the native. Those are variants. And Ember 3D can, to some extent, predict this change. That's a nice image. What the next 2 slides are going to show is the statement that on average, when I correlate the Ember prediction, so on the one end, what I'm going to do is I'm going to predict sequence variant effects. So for every single position, I'm going to do native against 19 non-native. And I do that at every single position, one at a time, for the entire protein. And then I correlate predicted structure change with the experimental function change, because there's not enough of predicted structure change. And we see a correlation that is way better for Ember 3D than for AlphaFold 2. Okay? Now we have a problem with that, and that is sort of something that came just a few days before I came here. We still don't quite know how valuable that is. So what we have learned, and that was the discussion also yesterday about dynamics, we do not pick up big movements. That we know. And we are still trying to sort of nail down how good we actually are with small movements, but we clearly have a correlation at this point. We don't know how meaningful that correlation is, but that is the measure by which methods that predict the effect of sequence variations are all assessed. And by that, we are not as good as the specialists because we predict structural change, not functional change. Anyway, so there's maybe, we believe, we're trying to sell there some information, important information in it. If you took that, and again, I have some doubts now, but I still believe in it, you can make movies. What this movie here shows is where you see the blue is the position at which, for 1 second, all 19 non-native structures are predicted. So looking at the movie, essentially see all the sequence variations in a protein. So when Konstantin can do that, he has to bring his old laptop, and he can do that in front of you. In fact, this prediction here is faster than the rendering. So he makes a lot of photos, then he sort of assembles these photos, and the assembly is slower than the prediction. on an old laptop. So this is by computing, right? Again, we have to see, by the way, this is the same thing as the distance map that also changes slowly, and that's sort of the predicted average effect. You see some positions have a stronger effect. So clearly, with these PLMs, we can sort of sit on the side of individual things, we can sit on the side of bicomputing, and we have individual predictions, because we can see, to some extent at least, the effect of variance. The next two slides are going to be about protein design that I skipped because of time. I'm sorry for that. Now, I want to still put in this important point, I believe, this issue of homology-based inference. So you have experimental data for protein A, and protein B is similar in sequence to protein A, so you infer that protein B has the same feature, whatever that is, protein interaction, protein structure, whatever that is. That's homology-based modeling for protein structure prediction. Most annotations in databases are based on homology-based inference. Many of those are labeled as experimental annotations. They are not. So that depends on the value or on the quality of the database. But by far, most existing annotations are homology-based inferred. Now, again, as much as fold-seek sort of replaces alignment, these embeddings now replace the idea of homology-based inference in the sense that we can now, rather than looking sequence identity between two proteins, we can look at the embedding identity between two proteins. The advantage is this is way faster. What this story here shows, you can sort of predict Go categories with that. It's not the world's best thing, but by far the fastest. And it's, at least at CAFA, it was in the top 10. Here's another story from Michael Heinziger, where he has a tool that predicts, he essentially changes these embeddings through so-called contrastive learning. He improves the embeddings to be specific for CAF predictions. That's 5 minutes. Now, the 5 minutes got me out. Let me give you 2 examples for how you can use it for per residue prediction. Here's the first. Predicting protein disorder. Again, that's sort of the recent Chi competition. This is a tool that was stitched together. It's relatively simple. And it's not the top method, but it's one of the top methods. By some criteria, it's the top method. It's way by far the simplest and the fastest of these methods that predict aspects of disorder. There's another example where it really works. Here's yet another example, and that is binding prediction. So Maria Littmann tried to predict for a particular residue whether it binds another substrate, anything other than protein-protein binding. That we kept out of here. All the other binding residues, right? And in my history of protein structure prediction or function prediction, I always looked at sliding windows. So I predicted the effect at the central residue position here given the environment of the other amino acids, right? We didn't have enough data here. We could not even do one-hot encoding. We could only use 8 input units. So we had to find a clever way, go back to the olden days, 30 years ago before alignment information, and sort of engineer a good way of using information. And then we got something that was clearly better than random, was clearly better than anything that existed, but was not good enough for us to we published it, but we did not put that online. So then we had the idea, now let's try it with embeddings, and now the database has grown. So this is the growth of the database of unique proteins. So for 46 unique proteins in the scale of almost 2 years, experimental data was added to any organism. This is not human, right? For 1,500, there was some data added, but most of those are within the homology-based range of all the others. Only 46 were unique. So we did not have more data, really. Nevertheless, these embeddings work like a charm. So I told you we could only use 8 input units. Now we use 1,024. But they are so informative about protein interaction that, in fact, they sufficed. And in many cases, this system, which is not a big CNN or anything like that, it's a relatively simple machine learning device, learns in some cases, and one is shown here, better than the teacher. So examples where the teacher said this is not binding are predicted with a high reliability as binding, and they're correct. So there's a lot of other evidence that we found afterwards. When we look at the entire proteomes here, human, you see that a lot of the annotations that you have about human come only from this method. Only through machine learning. I get back to that point. Science is communication. This is the great place to do that. Thank you for making it happen. But PLMs for me are sort of the space where we can sort of shine as individuals, where we can really have small computing, and I feel this is important. I believe the discussion about how much accuracy am I ready to sacrifice for gaining energy is a discussion that should start today. And we are specific to particular proteins. So it's a great example. So if you see sort of everything under AlphaFold 2 as the marriage of AI and evolutionary information from the method that predicts secondary structure to the method that is AlphaFold, the breakthrough was using alignments. But that's over. Now, understanding the language of life, the PLMs that implicitly code for that, that is the next step forward. There is absolutely no novelty that we can discover without machine learning. The repetition of homology-based inference is something that has hindered us in being faster for many years. So it's time to change that. I also know that loads of nonsense is done with AI. Maybe it's even true that most of the AI publications are nonsense. May very well be true because it's not easy, particularly for protein-protein interaction. I'm sorry that I was so vocal, but the preparation of the data set, I've done so many things in my life. That's by far the most complicated one. We still keep stumbling over it. Speed may translate to fewer resources, and that may be what we really care for. I'm somehow sorry that I have such a fast talk. I put a lot of papers in there. This is not to show you that I can write a lot of papers. Actually, it's anyway the students who write them. But the point is, we have tried that on so many things already. Try your own tool. We actually have an interface where you can sort of plug in whatever data you have to try embeddings relatively simply. The biotrainer. Thank you very much for your attention. Particular thanks to a bunch of people. The group, I just want to mention Anna Tramontano, and to the people who organized this meeting. Thank you. I'm sorry for being so much over time.
No, that's fine. Thank you very much. Any questions for Burkhard? Lots of questions.
I have a stupid question as a person who looks to sequence alignment sometimes. So I have the proteins, I have a sequence alignment, I know like some active residues in one protein and transfer them to another one according to the alignment. How can I do it with these embeddings?
So that is more complicated. So for that one, I believe at some point I have to refine. I'm provoking too much, and then why do you put your finger exactly on that one? So you can replace alignments and do an embedding-based alignment, and in fact, it does it better, but it takes a lot of time. So that is like going back to the Smith-Waterman days. So this is better than MM6, for instance, but it's not worth it. What I really meant is predict structure, do the structure alignment, use fold seek, use those, and then you align afterwards. Maybe I shouldn't have said alignments are over, but the finding part. So finding the homologs, that is handled by that. Again, there's an answer for what you say, and we are working on getting that better. But at this point, so far, we have shown there's a publication from, I don't find him now. So it's Martin Steinegger and here, Konstantin Schützer, is a recent publication in which they show that, in fact, you can do the alignment, and that does actually do better, but it takes a lot of time. Sorry, next question.
So it's more related to the map that you showed, like the heat map for the mutation. I mean, when you look at DMS experiment on MAVE, I mean,
the one that I didn't show.
The one did you show? Like, I mean,
yeah, I skipped over it. Yes. Anyway, your point is?
I mean, clearly, like your model don't capture everything because usually those map like contain 60% of like mutation that compromise the stability. Did you ever like assess how much?
So is it again as a judgment call? Which ones compromise stability, and what is the reason for compromising stability? How is that related to function? So the short answer is no.
Okay,
obviously.
but there are like I mean, for example, if you look at one set, then in theory, in cell abundance, you can in theory like.
But the stability, 60% stability is based on some thresholds, right? So whether that is 60 or 20 depends absolutely on your threshold. So that depends on what you call exposed. Do you call 0% exposed, or you call 50% or 16% or whatever? That's exactly where this problem starts. So what number you throw at me depends on that assumption.
Okay, let's say.
That makes it complicated.
I will call when the protein is degraded.
When the protein
is degraded by the system. So that's when you expose something that shouldn't be exposed.
But then you ultimately need experimental data for it. Anyway, we don't have the answer for that.
Okay.
What I can tell you something else, and that again is a very new finding and very shocking for us. You can ask, so let me just look at the extremes here. That is the predicted effect here, that's for AlphaFold, and that's the observed effect. So you can ask the ones that have a stronger effect or very weak effect, are they doing better? And it turns out, that's why I said it's not good at strong effects, it turns out for Ember3D it's not the case. So when you look at the more extreme ones, Ember3D actually falls in performance. Does better for the small changes.
How small?
How much?
How much small, like how much?
Yeah, so this answer is a little bit complicated by the fact, so we have done that only for 5 proteins because we can run the entire AlphaFold, or collab fold in this particular case, only for 5 proteins because we don't have enough resources. And on 5, the number is not in the statistical significance number, is that right? Or is it above the statistical significance? It is. So it is statistically significant, but relatively within that reach, right? And Konstantin is redoing it for a larger set, which we cannot do for AlphaFold, but at least for his method. Sergey?
May I ask you why the training procedure of protein language model is not so different from the natural languages? Why still 15%? Why still absolutely the same architectures?
That's a similar answer as the one with the money. Because we essentially don't have the resources to optimize all of these parameters. Very simple. So what you could imagine is that you optimize on Swissprot or UniProt, because that is so small that you get a fast answer. But the problem is UniProt is not giving us what we need. So there is when I go back to the slide where I showed that you had to go through a certain number of generations here before we reach the state of the art. This is exactly it. With this, we don't get the state of the art. And then to say, I use that as a proxy, could be completely wrong, right? So we cannot optimize on a small data set. And for the bigger data set, we at least don't have the resources. There's another tool that we just published or put on bioRxiv called aix, that uses the T4 TPUs from Google. So that went a little bit closer to optimizing more. And there's some evidence that it pays off, but it's still nowhere near sort of putting down these big numbers, rewriting the program. It's just not the resources. Yes? Thank you, Wouter.
Thanks a lot for the great talk. So I wanted to ask you a general question. So I've heard a couple of times this argument that language models are supposed to, capture the evolutionary information by training on the, no?
I don't believe so.
Okay. Because what do you think?
We are writing a manuscript in which we claim this is not the case. And this manuscript we have been writing since 1 year because we're adding experiments, and every single time it looks as if. But, and there's a discussion I had this morning with Johannes, and he says it doesn't matter. For me, it's a difference. So I believe, but I cannot prove it, I believe that language models can capture biophysical constraints. Evolutionary information also captures biophysical constraints. I believe they capture the same thing, but they are still different. So I don't believe they can capture evolutionary information. And if we had more time, I would explain why I believe that.
Okay. One more question. Do you think it makes sense to add this, let's say, multiple sequence alignment in training language models?
Yes, absolutely believe that it would make sense. But then it worked. So that is part of the paper I was talking, or the manuscript that I'm talking about. So it worked for the old generation. Since Prot T5, it no longer works. And we tried 5 different ways of putting MSA information into the protein language model. So not building the protein language models on evolutionary information. What we essentially tried is to use the evolutionary information as an averaging tool afterwards, right? We predict for embeddings, for instance, 3D structure, we average, or for secondary structure, we average, right? And until prot BERT, this worked. In prot T5, that turned around. So now you can argue that maybe because you have reached the ceiling, or it captures evolutionary information, which I don't believe it does, but we are in the circle. Sorry for the...
Thank you.
Okay, I think in the interest of time, we have to stop the question session here. So let's thank Burkhard again.
Sorry.